We're still in the big lecture about mineral physical properties in pages 19 to 36 in the textbook. But now we're moving on to the second big heading, which is interactions with light. And in this one, we're not going to draw so many things. Instead, I'm going to throw in pictures. And it's like a lot of pictures, and I mean, most of them are coming from places like Wikipedia, so there shouldn't be any copyright issues. But with interactions with light, our eyeballs are our tools. Eyes are tools. And we have to train them to see light that is reflected, right? So if here's our surface, we can have light that's coming inbound, right? That's called our incident light. And that incident light can either be, okay, here we go, draw it in, come on, pen, there it is. It can be reflected. It can enter the material, bounce off surfaces within the material and exit, and that's called refracted. And light can also then pass through the material, which is called transmitted. In each instance, some of the light can be absorbed. And when that light is absorbed, we see different colors than what the incident light was. So as we go through these different interactions, we're going to start talking about transmission, and then we'll go to luster, color, streak. These are the topics for today. So with transmission, this is like a degree, an amount of light that gets passed through a material. And gemstones or minerals have different amounts of this. Things can be transparent, where the transmission amount is full transmission. Things can be translucent, and things can be opaque. All right, so opaque is easy. There is no transmission. Where translucent is the intermediate, and here we have its diffuse transmission. There's no sharp outline of like the object, but things kind of look hazy. So diffuse and hazy will be the words I'll write down here. Let's just look at 3 pictures of different amounts of transmission. Here's a spinel crystal. This spinel crystal, cover? Oh boy, just fit it in right here. You can see right through this beautiful pink crystal, so much so that you can even see this unusual inclusion sitting inside this octahedron. Opal is a really good example of diffuse transmission, where that's translucent. Light's coming through, but you can see things are looking a little cloudy. And now here's an example of jade, where there is no light at all that comes through the jade. It's all absorbed, and it's giving you this color. All right, let's move on to luster. Luster is an important one, especially for metallic minerals. Luster is the appearance of the surface and reflected light. It's not exactly color, okay? It's like, how does that light bounce off like a mirror and come to your eye? There are 2 main types of lusters. One is called metallic, all right, and it looks like a metal. Metallic, there's only one I in there. And let's say that these are opaque minerals, and they have a polished metal surface. They can occur in a variety of different colors, from gold to silver, etc. Here's an example of pyrite, where you can see that golden metallic luster. But there are many different adjectives that can be used for non-metallic lusters. And again, as we start using adjectives, then they're kind of variable. So let's just say variable, and as I introduce these adjectives to you, know that you can use things somewhat interchangeably depending on what your eye sees. Why don't I go ahead and write down all the adjectives, and then I'll throw in pictures. We're going to go from most brilliant non-metallic lusters all the way down to really dull surfaces. And so let's just go through. Here we go. There is adamantine. This is like diamond. It's incredibly brilliant and bright. Next is vitreous. Vitreous is glassy. Not quite as shiny as adamantine, but still beautiful gem-like crystal quality. Resinous is when things are starting to get a little bit dull, and it looks like waxy or resiny. Then there is pearly and greasy. These have a bit of a sheen to the surface. So pearly, we tend to say like there's a sheen to it, whereas greasy kind of looks oily. And I would say they are not part of the brilliant to dull transition so much. They're kind of like little outliers from this. Silky is another one that kind of has a play of light on the surface. And then finally we get down to earthy. And earthy is just dull and no like reflectance of light at all. So silky is like satin, and earthy, this is when the crystal form is massive, it's almost always earthy. When the luster is silky, you almost always have fibrous crystal form. So let me show you some pictures of these different things. Here is a picture of talc. Talc has a pearly, non-metallic luster to it. Here's an example of amber. And amber has a waxy, resinous luster. What else do we have? Here's another good example. This one is a silky. This is a tiger's eye, which is a variety of quartz, and you can see a silky luster to it. And well, I'll be darned if I didn't put an example of adamantine or vitreous, and it would be something more like this variety of spinel. Okay, that's your introduction to luster. Now let's move on to just straight color. What is this? I think this is big C. Big C is color. And to start color, I want to just say one thing. We've got to be careful, right? Because something like 4% of men are colorblind, where reds and greens start to be hard to see. And so if you look at these circles, those of you who don't have colorblind difficulties can see a 12 here, right? And then, what is this one? 74, 6, 42. I think this was the one I struggle with the most. I think that's a 2. And if you didn't see those colors, then there's a good chance you have red-green color blindness. And so using color as a diagnostic property of minerals will be confusing to you, because some people might be using words that are different than what you actually see. And that's something you'd want to talk with your professor about. Next thing I don't think there's anything else really to say about color. I guess we could say this, that metallic colors tend to be diagnostic. Metallic colors tend to be diagnostic, right? Copper is copper colored, gold is gold colored, but you do need to look out for tarnish. So tarnish can occur on the surface of a metallic mineral and make it be change its color. And then for non-metallic, well, it can be diagnostic, but it might not. So you just have to be careful. Something like quartz can occur in every color of the rainbow, but something like sulfur is a diagnostic yellow color. So it's just something you have to learn as you go through those minerals. All right. Next interaction with light is called streak. And streak is the color of the finely powdered mineral. Color of finely powdered mineral. It is sometimes incredibly useful as a tool, as a diagnostic tool for identification. So here's an example of pyrite being scratched on white porcelain, leaving behind a black streak. You know what's unusual about that? Look at the color. Pyrite is gold, right? But its streak is actually blackish with green specks. So the color of the finely powdered mineral is not necessarily the same as the mineral itself. Here is, I believe, rhodochrosite, and it leaves a white streak, even though the mineral itself is pink. So a couple rules of thumb with streak is that Metallic minerals, this can be diagnostic. Or let's say like this is helpful. A great tool for identifying unknown metallic minerals. However, in non-metallic minerals, the powder tends to just be white, and so it can't be used. The other thing I would say is that you can never use streak on something harder than the streak plate. So you can't find the streak of a diamond because it won't break apart in powder on this material. So only minerals softer than 7. And if you don't know what I'm talking about when I say Mohs hardness in 7, that's because I haven't introduced it yet and it's coming in the next lecture. So that's a little embarrassing for my order of operations here. D, so next is E. We're going to start to get into some of the more complicated types of interactions with light that are less prevalent but very interesting. Play of color is also known as opalescence. Opalescence. All right, and this is what we see in opal. The idea, let me just show you a beautiful picture of opals and then give you a picture to describe what's going on to create the phenomenon of opalescence. In this sample here, we see a stunning opal that would be worth much money because it has all these different colors in the surface. And here is another opal that's dull with no play of color. And the reason behind it is because the structure of the non-beautiful type is disorganized. Disorganized. Whereas the beautiful play of color opal has a distinct structure to these spheres, which refract. Which refract. Did I say refract 2 times in a row? I meant to say diffract, which diffracts light. And so the main process to get play of color is we have diffraction splits light into glitch in here, splits light into many wavelengths. And when wavelengths, that just means color, right? Those are synonyms. And so what ends up happening is that it's these surface imperfections in the mineral that create the opportunity for diffraction. In opal, the diffraction, so we're just going to say this, in opal, diffraction occurs off of organized 150 nanometer, that's the size of these things, spheres that when the spheres are bigger, they produce colors like blue. And when the spheres are smaller, the bigger ones produce reds and the smaller ones produce blues. An equivalent of this is the spacing on the back of a CD, which is kind of an older technology now. But if you take the back of a CD and move it around in light, you see many different colors, or an oil spill on the road. So an opal diffraction occurs off of closely packed spheres in structure. The equivalent is grooves on back of a CD. We don't see play of color in very many minerals, but there are in some. So opal is one, and then the other example that we're going to see play of color in is a type of plagioclase feldspar that's called labradorite. So the other example, so we have opal is one type of rock, and then another is called labradorite, which is a type of plagioclase feldspar. And it's a very common type of mineral, plagioclase is, and maybe you've seen this like even in kitchen countertops. We will take a rock, hold it up to the light, and we see nothing. It's just a dull gray. But if you move it just slightly, you'll get a beautiful play of color in the same exact specimen. And that's because there are little grooves. Well, they're not grooves. They're twin planes. There's little like twin planes inside the crystal that incoming light will bounce off of and diffract, creating a play of color. All right, we're almost done. There's just two more things to get into. What was that one? Was that one? E. Okay, so we have F and G left to do. Then F is going to be chatoyancy. Chatoyancy. Now we're in the special kind of categories here. Chatoyancy is a band of silky light reflected off of packed and aligned crystal fibers. What does it actually look like? Well, in gemstones, we see chatoyancy from time to time. In this example, these are star sapphires. And the star sapphires have this optical effect where you get these bands of light. So when I talk about a band of light, I'm talking about this 6-rayed star. And it's because there are a bunch of fibers of rutile, little needles grown inside the sapphire that reflect light, right? And so they're controlled by the hexagonal crystal structure, the orientation of the rutiles. We're getting a little too deep here, I think, in the content. But we have these rutiles that are very, very fine-grained, grown along the crystal structure. Let's see, can you actually see the crystal structure? You actually can. Look at this right here. See that? You can actually see part of the hexagonal crystal structure in these polished gems. But what we get is a band of silky light reflected from fibers. Reflected from fibers inside the crystal. All right, and the fibers must be aligned. So maybe let's put that word here. All right, from aligned fibers in the crystal structure. I've actually shown you. Here we go. Here's another example of a chatoyancy creating a tiger's eye effect in quartz. Okay. Man, a lot of beautiful pictures in today's lecture. Now the last thing to talk about is called luminescence. So this is G. Luminescence. Let's try to spell this correct. Luminescence. Luminescence is visible light that is produced and given off from a mineral. And it happens in a variety of different ways. You can well, fluorescence is our best example, and we'll talk about it. So let's say visible light emitted from a mineral in response to it absorbing energy, in response to energy being absorbed. The example we're going to go into is the process of fluorescence, but it's not just fluorescence, which is UV light, okay? So when you put UV light on a mineral, you can actually get the mineral to completely change color and look amazing. So if you have short wave, so here it is, and here's a mineral in visible light, and it's just white. And then if you put it under high wavelength UV, we get a certain amount of colors that are emitted from the same mineral. And if you change it to short wave radiation UV light, you get other types of energy back to your eye. Well, you can do this in a variety of other ways as well. You can take rocks and hit them together. That's called mechanical luminescence. You can heat minerals, you can take fluorite and put it in a frying pan, and that fluorite will release light and start to glow on the fry pan. That's called thermoluminescence. There's a lot of different types, but let's just talk about fluorescence as an example. And to do it, we have to think about the orbitals inside of the electron shell. So let's draw a couple electron shells, and here is our ground base state. And there's an electron sitting here happily and content until incoming UV energy hits it. When that UV energy hits that electron, it excites it and makes it jump to a higher orbital. So we're going to go higher orbital. And it can do this because it's absorbed some of the energy from the UV. Well, it's here, right? But it's only here for a little bit of time. It's not stable here. And so what it does is it has to drop to a lower orbital. And as it drops to that lower orbital, because it can't stay at the higher orbit, it's going to be able to, it has to release its own energy in the form of visible light. So that's our schematic for how fluorescence works. And so I guess if we were to like put notes on this, that first step is that the electron absorbs UV energy, right? And then next step is that it jumps to higher energy orbital. But it can't stay there. But it can't stay there. So instead what it has to do is it has to fall. And it's going to fall to lower energy states. Okay, so let's say fall to lower states, and the fall releases, right? It actually requires it. It requires the release of energy and it might be in the amount that's like in the visible light range. And when it happens, that's when we can see it. So the fall releases energy in visible light range. And that's how fluorescence works. There's other types of fluorescence. There's even there's one type of fluorescence called phosphorescence. Phosphorescence. And in the way that it's different is that there is a time delay on this one. With fluorescence, this happens like immediately. You only see the color when the UV energy is hitting. But when something's phosphorescent, the process of going like from the higher orbital to the lower orbital to the lower orbital to the lower orbital actually takes seconds to minutes. So your object will glow for a period of time.